Revising DFS as well as binary trees. First thing to note that every binary tree might fall like 99% of the times into this template only. The template has some global variables on top on a requirement basis, a DFS algorithm to traverse it, and the parent function, which is the caller of the DFS algorithm. Again, global variables are on a requirement basis. It might be the k, it might be a map, it might be a vector, it might be an answer that is to be returned in the parent function. In the DFS, a root is mandatory and other arguments are on a need basis again. The first line is always present as if not root, return. Then there is some pre-processing. Then there is traversal, which is the processing part. First part, this is the processing part, and then there is post-processing part. After post-processing, we just return. In the return of the parent function, there are two types of returns basically. One is wherein we just do a DFS on the root using the DFS call only. The second is wherein we do the root DFS, but we also call in their left subtrees and the right subtrees with the same parent function. So that we are saying that for each and every subtree, consider that root to be the parent, and we are saying that whatever we are considering in the algorithm. So suppose we want to know how many subtrees have some value, right? So that value, should it start from somewhere? And if it starts from that particular node, right, we are just saying that this root right will get replaced by roots left and roots right. So consider every root as the root, in the sense consider every node as the root and do all the iterations. So basically it is consider every node as root. Coming back to path sum, here we have to just return a boolean stating if some path is equal to target. Some paths sum is equal to target. Now there is a simple code like 2 to 3 lines code wherein we can just over here only in the parent function only directly we can return in the DFS itself and have the DFS as boolean. There also we can do the same thing, that we can just have the right subtree or the left subtree. If root value equal to target, if the roots value equal to target, we say that okay, we have reached it, we have reached the sum, right? So we will say that we have reached the target sum and we will return true in that case. Or else we will just do a minus of the roots value from the target sum, so that target sum is this, and this target sum should be always decreasing and it should reach a point wherein at a leaf node we should feel that this is the condition for the leaf node. At a leaf node we should feel that our condition to be met, and when this is met we are saying that it is true. Over here also it could be done, could be directly passed. In the sense we can just over here return DFS of root comma target, and then inside we can just have return of the left subtree or the right subtree if the roots value does not match the sum. If it matches the sum, directly return, there is no any problem there. So this is path sum 1. Path sum 2 is just a subtle variation of this one. Here only one thing to remember is that whenever we are here, just we have to return the path also, return path of that sum's target. Like if some path sum equal to target, then we have to return all those paths inside a vector of int array, right? Now two things to note over here. One, whenever we are considering this type of thing, we can just take a global variable and then try filling it whenever we meet the condition. When do we meet the condition? If it is a leaf node and the condition of target sum is met. leaf node and the target sum is met, then we'll just push it into the array. Now what over here, if I see the code, I'm just passing this array which were declared here, and this is a temporary array. This just considers so that we should be able to push it into the stack. And then here also we can just ideally return. That got cut off in the SS. Return is also there over here. So now we are just saying whenever this thing happens, we should just push it back to the stack instead of returning a true or false value. That is it. And how are we updating it? We are just updating it via this line, wherein we first push in the roots value and then we process, like we check if the sum is equal to roots value. If it is equal, then we just push that stack and return. If it is not equal, we go to the left subtree and the right subtree to check whether is there another leaf node in that particular DFS wherein we can get the answer, which is being done by here. And then both sum and array by value we are passing here, so we don't have to worry much about it. If we passed this array by reference, then we would have to add two lines over here. One would be over here wherein we would do array.popback, which is the backtracking part. If and then I had to do this, plus I had to do this also over here also, array.popback before returning. So these two lines would have to be added. Apart from that, this is the same path sum 2. Path sum 3 is a bit more challenging and complex, because it is not exactly complex, because the unoptimized or algorithm also we can do it. In the unoptimized algorithm, what we say is we have a target sum over in this question, and then we just need to find out those particular paths wherein we can get the target sum, and those target sums have to just be contiguous nodes. It can be anywhere in the tree. It does not have to start from the root node and end at the leaf node. It can be anywhere in the tree. So that is the constraint over here. Now over here we can just say what we can do in the brute case scenario is we will just consider that suppose I will take that my 10 as the start. I will consider that let it be the start, and I will check is there something to the left and to the right which can give me the target sum, right? Is it? Then we can pass it. Or else I will just go to the roots right and the roots lefts. I will go to the root right and I will just call this same function again. Over here, if you see, I'm calling the same parent function. Now what this is doing, this is saying that let me be the start now and let me check. And what this part is doing is it is telling let me be the start and then let me check. Now if anything out of these is giving a true value, right, we know that we have found out something. Now the counts is what we need. So we would need the left's value, the right's values, how many they are giving. So it will be plus, and then the return type, we can just return it. And then in the DFS, we can just have a mere check that if the target sum is being reached. Over here, we will just consider the same sum, right? Because we are saying that we have considered the possibility when 10 was considered. 10 was a part. When 10 is not a part of path, then there are these two cases. Similarly, again, it will go on recursing, and it will become a exponential kind of a thing. Now, just to optimize it a bit, not exactly exponential, but for each node we will be doing n times operation. So it would be ideally like n square. So from n square, if we want to bring it down to n square to n, we can just have a very succinct approach of a prefix array, which is a very good approach I found out in the editorial. Now in these type of functions, one more thing is that we need to have a not root condition here also, because we are just going to the right, we are accessing the right one. It can be a null. The roots left also can be a null, so we just have to check in the parent function also, because over here we are just not saying that it is only calling DFS, it is calling itself also, and then DFS is calling DFS in itself, that is there, but here it is calling itself also first. With this root right can be null, right? This can be null, so check should be there. Next, prefix sum usage. So prefix sum, we just have some values, right? So we have, like, suppose I equal to 0, 1, 2, 3, 4, and the prefix sums would be like, suppose the array is 1, 3, 5, 2, 1. So the prefix sum would be 1, 4. Yes, this would be the prefix sum. Now if I want to say that can some subarray be equal to 3, can it be equal to 3? We have to check now, right? Now for checking, what we can say is, when we are coming to this point, right, we will just check now, is 4 minus this whatever target present already? It was present over here, so we can say we will have 1 over here, right? Now when we go over here till 12, now we will say, was 12 minus 3 present somewhere? Yes, it was present at 9. We pushed 9 also, right, in the map, so we have that in the map. So did we have a chance? So from here to 9 to, so 2 to 4, the contiguous byte excluding 2, we will have the sum as 3, and this one also we will have the sum as 3. The same concept will be using here also. Here also we are maintaining the same thing, but in the form of map. So first we are using a map to store it, next we are making it a global variable, next we are backtracking it. This is very important, because when we are going back, suppose when I am going like this to this, right, over here I have inserted in the map that map of 10 plus plus, right? When I go over here, I will do map of 15 plus plus, because prefix sum. I will go over here, I will do map of 3 plus plus over here. I will go here, map of 18 plus plus, map of 21 plus plus, which is like every value is 1 right now. Now when I'm going back, at that point I should remove this 21, right? Because this value, when we come here, this should not consider 21 as the possibility, should not consider 21 as a complement possibility, right? So we have to remove this also. So first we insert something, I mean when we are starting the process, before process, this is a pre-processing. In pre-processing we insert, then we process, then we expel it out again, which is the post-processing part. So that is how we do the backtracking, and then we are returning the type as DFS only. We can have a global variable also if we want, or else we can just return it in the form of this. Like, in the sense, what I'm saying is, we can either do this, which we are doing, or else we could have done this also and stored that answer as a global variable. We don't need to store the answer as a global variable, so it is fine. So coming to the code, we can see we just have global variables initialized. This is a long, and then default. Then we are doing, this is like the running sum. Over here, this is the value that is required by us, right? Running sum is the sum till now. Sum till now helps us to calculate the, helps us with prefix array. Now the prefix array nahi hai, this is the prefix map. Now what we do is, we first ideally add it add the current's root value to the RS, and then we look. So suppose we came till this 21, right? We came till 21 now. Now I have 21 in hand over here. What I should check for the target to have 3s? What should I check? I should check whether 21 minus 3 is present or not. What I am doing over here is, so in my list of 10, 5, 3, 3, can I remove some part from it so that my current should be equal to target? Can I remove? Is remove possible? If it is possible, then we can just remove it, right? And removal is possible when we know that the prefix sum till here was 18, right? And we have that it was 18. So we can say that 3, 18 will be reached over here. We can say that. What check? This check was done here. That current running sum minus the target should be reachable. This part can be negated out, in the sense if it was already experienced somewhere and we have like noticed that we came across this value, then we can just take out that part and then we can say that we have reached these many. But it is like map of count, right? So how many ever values it is going to have to like how many times we have seen that? We might have seen 18 two times also before at different locations. Now we can say that when we reach this location, we can directly say that the current answer would become 2, right? Next we are just inserting it into the map, then we are processing the left part, processing the right part, then we are removing it. This is the backtracking part. Then we are just returning whatever the current value was there. Now we are doing a current plus over here only. So what we can ideally do is, we can also directly write current plus equal to map of RS minus K plus DFS of root of left comma RS plus DFS of root of right comma RS. Over here what we are doing is, we are just, this considers all the possibilities that ending at root, how many are there? How many possible subarrays make target, right? This is that possibility. This goes on to check, we are considering that now get me all the values from roots left which will be equal to the target, provided it already has this running sum and it has the maps context, right? That what it has seen now. So those things, and then we can just return the value over here. This was the path 3 sum. This is a good question. Path 4 sum is like basically not, I would say, great, but it is fine. It is more like a math problem. Over here, how we represent it in a binary tree, we have to understand. So there are 3 numbers. This depicts the first number, depicts the hundreds position, depicts depth, then position, then value. So now we are just mapping position, which is depth plus position, as the key to the value. We'll just store it in a map so that we can access it in OAuth one time, and then we can just somehow have a link. To have that link, we know that we have some maths, that if the depth is this much, if the position is this much, the next left would be that one more depth, and then position would be 2 into position minus 1. So suppose there was a 1 over here, and then 2 and 3, right? And then 4 and 5. This is a complete tree. Now over here what can we say? Full binary tree. So the position is 2, right? what can this position be? Depth is, I would say, what would be the depth? It would be 1 right over here. Depth is 1, but what is the position? Position is 2 into the position, which is 1 minus 1. Similarly, what is the position for this one? We got it as the left one, right? This is the left one. So now this would be the left one and this would be the right one of this. So this has some D and P values, depth and position values. So now position into 2, position is already just 1 for it. So 2 into position would be 2, and then we would be doing a minus 1. So we would be getting equal to 1. So the position of this 2 is 1 and the depth is 1. Depth is 2 for this 2 because it was 1 over here. For 3 it will be just this left plus 1, right? So the same thing we are doing over here. We are incrementing the depth and intoing it with 10 because it is in that place. Over here we have to consider now, if 2 has to find out its left, it will do 2 minus 2 into 2, which is 4 minus 1. So the next part will anytime be 2 into 2 minus 1. So 2 into this is position is 1, this position is 2. Over here if I do 6 and 7, right? So that position will give me 2 into 2, which is 4 minus 1, which is 3. So 6 position is 3 in this depth. So position is relative to depth. Every depth has 1, 2, 3, 4, 5 positions like that. Again, it boils down to the same easier question afterwards. But this is main, wherein we populate the map such that it is 1, 1, 0. This is the root. This defines the root. This defines the position. This defines the value. And then having a left and right. How? 2, 1, 2, 2. 3, 1, 3, 2. 3, 3, 3, 4. 4, 1, 4, 2, and so on, because this is a full binary tree. Apart from this, the only condition was that over here, whenever we meet the condition that it is a leaf node, just whatever the running sum was there, this was the running sum, add it into our final answer. This is the final global answer, running sum. Leaf reached. If it reached, add running sum to global answer and return. That is it about path sum 1, 2, 3, 4. We have done path sums. Now there are 2 more questions linked to this only, similar to this. One is linked list in a binary tree. So we have to find out if there is some linked list present in the binary tree or not. Now the only corner case where my logic failed was what I was trying to do. I was going to each and every parent and saying from the parent function I just called root. I did not call its left and right subtrees. That was the first problem. And then to handle that, what I had to do, I had to start over here and then I had to manually call left and right. Now while doing that, what I was considering is if it is equal to head, I was moving both pointers. Like if this value equal to the linked lists value, I was moving both pointers. So what was happening is I was missing some cases, then that from here also we could have started. Right? So those cases were being missed. So if we consider that, then it is easier that we have to consider key only the root first as the start. Then we have to also consider its left and right as starts. and then I can just return that whether it is present or not. So that would be just based on the values, that if root is not present, then just return. If it is equal to head, this means if head is reached, this means we already know that we have reached end of linked list, and we have to return true. This is what we need. If we don't, then we can just return false. We can just club these two values, that if not root, and root's value not equal to root's head's value. If it is not equal, then we can just return false, or else we can go a further level deep while incrementing both. The problem with my approach was that I was considering this, I was doing this, but I was doing only this, and then over here I tried to handle these cases. While handling these cases, what happened was I was also considering those cases wherein 4,8 would be true, which is wrong. Optimization using KMP is present, but I was even afraid to look at it, so let's not talk about it. The last problem is binary tree maximum path sum. This is marked as hard, but it is a medium level hard maybe. Over here we have to just find out what is the maximum path sum from the total, right? Like whenever we reach like it can be anything, that path could be anything anywhere in that array. It can start from anywhere, it can end anywhere. That is the thing. Now what we can do is we have to just run a DFS, but while running a DFS we need to take care of what we are returning and what we are storing in the global variable. Over here global variable is very important. Global variable was declared default, just root is needed. Then we are just doing that, we are going to the left one and asking what is the maximum that left can give me, maximum path sum. Then we are going to the right, and then we are checking what is the maximum path sum that right could give me. And then while returning, so suppose if it is 1 2 3 4 5 6 7 8 something like this, right? 9 10. Now when we are going down, right, over here, while considering the answer could be this also, right? So we have to consider this also. Then we have to consider this part also. We have to consider all the possibilities. Now to understand this, what we are doing is, there can be only two cases. One wherein the path passes through the root, path passes through root, and the second one is path does not pass through root. Now if the path does not pass through root, it means that somewhere over here the path should be present, either in the left or the right. These two things will be taken care of over here in this part, and if any of these is negative, then don't consider it, because we don't want the sum to be negative, right? Over here this line, what it does is, we are considering that L plus R plus root value and then updating our answer. Over here we are considering this one to be a path, to be in the path. One is in the path, but in these both we are considering that one is not in path. In these both cases, same thing, we can see that the left best and the right best will already give me, considering that particular left's node and the right's node as the particular parents of those subtrees, and it will own and give me back what was the maximum from those subtrees. But while returning, we cannot just return L plus R plus root value, because from here suppose it came as 21, here it gave us 25. I need to return only this 25 plus 5 to 4, because 4 will say give me the maximum path that you can take. I cannot say that I can take both and I can do L plus R plus this 5 and then return to 4. This is not possible. I will take the maximum of these both and then I will return. So the return of the function and what we are storing in the answer in the global variable may not be same always. Yep, that's it.